My name's Andy Ramgobin and I am the CEO and co-founder of CodeZero. So we're here today to talk about a cutting edge showcase that we've done in partnership with AWS and Kaggle, the world's largest data science community. And this showcases a data set for deepfake detection. So effectively we've spun up a p4d instance in AWS, and we are using a test and train set from Kaggle to showcase our machine learning skills and our skills around distributed data parallel. So you can see here, again, just for transparency, we delivered this whole project within a week and we spent less than $1,200. So there's always a misconception that public cloud is very expensive, but when you know what you're doing and everything's optimized end to end, you've got an ability to do something very compelling for not a huge amount of money. And you can see here, these are our instances. We do have a Bastion jump host for secure connection. We've got a G6E, which is an L40S, and we've got our supercompute 8 to A100s, 96 cores, 1 terabyte of RAM, and a 400 gigabit per second network. So you can see here that we've got a Persephone A100 dashboard. This is using a CloudWatch monitoring script, a JSON file to build the dashboard, and then we're collecting metrics from things like Node Exporter and NVIDIA SMI. You'll be able to see here we've got S3 for syncing. This really helps us out in terms of uploading images, sample images, code bases from VS Code or our local machines to AWS and pulling them back for analysis so that we can work really strategically between our local machines and AWS. And I won't bore you with the myriad of different Python files that you'll see on the left, but this is a Python file for the last attempt that we ran, which was a NeRF, a neural radiance field that takes 2D images and creates a 3D scene. And you'll be able to see here as I'm scrolling through that we've got about 700 lines of code. So these aren't small, simple code bases. They're highly complex, and sometimes they require a lot of troubleshooting. You're going to see here a really cool image around training loss and learning rate schedule. This is exactly what you want to see as a data scientist, especially from a learning rate perspective. As we're running through those epochs, there's no huge oscillations. There is a divergence or convergence, I should say, of the model. And this is where each epoch, the model's learning and fine-tuning itself, and we're getting that stability that we're looking for. So now you're going to see a load of images, this one particular from an NVIDIA SMI that shows 7 GPUs at 100%. And you'll notice that one of the GPUs was at 0%, and that's deliberately. So we're using things like rank 0 to use a particular GPU to be the coordinator and the housekeeper for the GPU cluster. What this means is that we sacrifice the power of one GPU to make the other 7 run at 100%. So 7 GPUs running at 100% is better than 8 GPUs running at 60 or 70%. And you can see here again a ton of different CloudWatch metric screenshots that I've taken to showcase that we're able to use DDP and NVIDIA NCCL libraries to effectively distribute a data set across 8 different GPUs, train it, and get the results that we want, which is not always achievable if you don't know what you're doing. You know, more compute, more data doesn't mean a higher accuracy. You know, there is a scale where you need to really understand the data set. And you can see here, this is an image from our WGAN, which is a Generative Adversarial Network, a Wasserstein version of that. And this is where you've got a discriminator and a generator generates realistic photos based on the training data. And the discriminator has to discern whether these are real photos or whether they're fake photos. And I'll talk about in a little bit more detail without going too in depth what we did and why we did it. And again, some really cool images that, you know, these are really more for data scientists, but you know, it's just proof that we did exactly what we said we were going to do. And now you're going to see an HTML showcase, which really culminates in a week's worth of hard work. So 11 attempts, 8 GPUs, 6,400 generated faces. Best accuracy in a week was EfficientNet, and that was at 78%. Now, of course, we could get that accuracy higher, but for this project, within just a week, we really wanted to show convolutional neural networks, which was ResNet and EfficientNet for us, GANs, which was deep GAN and Wasserstein GAN, and then a NeRF model. And you can see here all of the AI and ML frameworks, Python ecosystem. This here is our research attempts. Again, we run it, we prove it, we benchmark it. You can see every single attempt that we've done and the breakdown of that attempt, the hardware it was run on, the date it was run, the results of that particular attempt. So this is really a detailed showcase that, you know, really kind of tells people what we did, why we did it, and how we did it. And you can see here a ton of different information here around distributed training. Our storage architecture was EFS for the dataset, EBS for persistent, and NVMe for scratch. If we'd needed to, we could have gone for Lustra and deployed Amazon FSx for true HPC, you know, millions of IOPS on scale out files, but we just didn't need it, and there was no need to over engineer it. And that's it. This is our project, deepfake detection, in collaboration with Kaggle and our partners, AWS.